This is an example that is presented in a separate screencast where we expand a real gas from a high pressure into a vacuum. If this were an ideal gas, there would be no temperature change, but what we want to do is calculate using the Ping-Robertson equation state what the final temperature would be and the final pressure. And we're going to use a spreadsheet from the Elliott and Lear thermodynamics book. The spreadsheet is available online. And we're going to use Excel Solver to determine the final conditions. And so the initial conditions are indicated here. And these are obtained from the spreadsheet, which I will show shortly how that was done. And then the final conditions, our answer, as presented in the previous screencast, are here. We've used the first law for a closed system to say that the internal energy does not change between the initial and final conditions. So we're going to use the spreadsheet to find the temperature and the pressure at the final conditions so that the internal energy is the same. And we're going to do that with the constraint that the volume, the final volume, is going to be 4 times the initial volume, because the vacuum volume is 3 times the initial volume of the gas, so the total final volume is 4 times the initial volume. When we do that, these are the final answers, and what I'm going to do now is lead you through the spreadsheet and how we use Solver to do this calculation. So here's the Excel spreadsheet, and what I've done is put in our starting temperature in yellow and starting pressure in megapascals. And in the spreadsheet, I'm on the properties page. So what I first need is the critical pressure and temperature and eccentric factor to do the calculation. And so if I go to the critical properties list, here are those values, which I can then copy and paste into the previous page. Other things that I need now are the heat capacity constants. And again, ideal gas heat capacities on this page for ethane. So again, I'm going to copy and paste those values. And so now the spreadsheet has calculated the initial internal energy, which is in blue, joules per mole, and the initial volume, which is in green. And notice that there's 2 possibilities. There's a 3 root region and a 1 root region, and we're in the 1 root region in this case. So we now have the initial internal energy, which was listed on our starting page of the screencast, and the initial volume. We want to have the final volume being 4 times the initial volume with the same internal energy, and we're going to change both the temperature and the pressure, and we're going to use the Excel solver to do that. So first, for this particular spreadsheet, the Elliott and Lear spreadsheet, I'm going to go into review, and originally it's protected, and I've unprotected it. So if it says that it's protected still, you want to then unprotect it. And now I'm going to, in data, use solver. And so solver says, first I want to set my objective function, and that's going to be my internal energy value. So that's here. That's what I want to have a value, and I've already typed it in, 2117.5. And now add the constraint. I'm going to put in my constraint, which is this value, and I'm going to make it equal to, and I will hit OK. Now I have the objective, constant internal energy, constraint of volume. I'm going to put in what cells I'm going to change. Now, it hadn't already be in there because I ran this before, but what I would then do is select these 2. So I'm going to change these 2 cells to end up with conditions the same internal energy and 4 times the initial volume. And now I hit solve, and it says that it's found the solution. I tell it to keep the solution. So now in yellow are the final conditions. So notice internal energy, same value. The volume is 4 times. It says my final temperature's decrease is 391.2 Kelvin, and the final pressure 0.65 megapascals, or 6.52 bar. Solver makes it very easy to do this type of calculation using this equation state spreadsheet.